This one is 2.22. Here there is a 35 meter flagpole which is having 20 centimeter diameter and it's made of steel. It is attached with a ball and socket joint for the support, and there are 4 cables attached here to keep it straight under the wind loads. So when in the beginning there is no wind, all these strings here, there is no tension in these 4 wires, and suddenly if there is a hurricane that comes and wind starts blowing, there is a horizontal force of 5 kilonewton at the mid height of the pole. So the total height of the pole here is 20 plus 15, so 35 meters. So the half of that is going to be 17.5 meter. So this is where there is an horizontal force that comes on this. So somewhere here we have this force P, which is 5 kilonewtons. We need to figure out how far the top of the pole moves from its original position, which was vertically above the base. So basically how far this point is going to move. This is what we need to figure out. So in terms of workflow, what we can do is, let's say this is our interest, this is what we want to find out. So we'll relate this delta to the deformation that will happen right at this point where all these wires are connected. So we'll find out this delta 1. Now this delta 1, we'll try to connect this with, let's say, this wire right here, which is AB. Now this delta AB, we will find the force FAB in this wire and relate this FAB with this force 5 kilonewton. That's how we can go back to this delta. So that's the workflow that we are going to follow. So first thing first, let's start thinking in terms of forces. So what is the role of all these 4 wires? There are 4 wires because we are expecting a wind to be going in any direction, and if the wind is trying to pull this pole, say this way, then this wire comes into picture. If it is the opposite direction, if wind is going this way, then this wire will start playing a role. Similarly, sideways motion, these 2 wires are going to be playing an active role there. So in the current situation, when the wind is blowing in this particular direction, if this point moves slightly to this side, this wire right here will have a reduction in the length, right? And since this is a wire here, it's going to slack, so it's not going to provide any tension there. Now similarly, these side wires here, although they will have tension, but their tension is going to be much lesser compared to this wire right here. So the majority of tension when this point moves to this direction is going to be in this member, which is AB wire right here. So now if I take your flagpole separate and look at the forces on this flagpole, because of the ball socket joint here, there may be reactions in X direction, Y direction and Z direction, okay? And then this force right here, which is right at the center, so this P value, which is 5 kilonewtons, and looking at from this side right here, there will be this force, which is FAB. And now since this angle right here is 45 degree, this is also going to be 45 degree, because the height on both sides is 20 meters and 20 meters. That's why this is going to be 45 degrees there. So if I do the moment balance about this bottom point right there, I can see that this FAB can be divided into 2 components, where your F cos 45 will pass through this point and FAB sin 45 will be horizontal. So your FAB sin 45 degrees into this total height, which is 20 meters. This moment will be balanced by your force P, which is 5 kilonewtons, acting at a distance of 17.5 meters. So from this we can calculate the value of FAB, which comes out as 6.18 kilonewtons. Now once we have the value of FAB, we can find the delta AB in this cable. So it's going to be FAB times length of this cable is going to be slanted length, which is 20 square root 2 meters, divided by EA. E is elastic modulus for steel, 205 gigapascals, and the cross section area. So cross section area, the diameter is given as 1 centimeters, so pi times 1 centimeter square divided by 4. So if I substitute the value of F here and calculate this delta AB, your delta AB comes out to be 10.87 millimeters. Now let us try relating the deformation in this cable AB with the horizontal movement of this point A, which is A dash, and which we have earlier defined as delta 1. Okay, so if I take this triangle and draw it separately here, so this is your final position of A, this is the original location, this is A dash, and this one is B. This right here is your delta 1. So in an approximate sense, if I draw a perpendicular line from here, this length AB is going to be same as this one right here. So this difference that you see here in lengths of A dash B and AB is going to be your delta AB. Now what are these angles? We know that earlier this angle was 45 degree because of this 20 meter here and 20 meter there. So if this is 45 degree, this is also 45, and this one is also 45. So now let me separately take out this triangle right here. So if I draw that, you can see that this angle is 45 degree. The slanted length is delta 1, and the base here is your delta AB. So from here you can see that delta 1 sine 45 degree is delta AB, or your delta 1 is equals to delta AB square root 2. Since delta AB we have already calculated, your delta 1 is 15.37 millimeters. Now let's focus on the pole. So originally your pole was vertical. Now it has to pass through this point because this is how it has deformed. So now if you see this top point right here, this is what we are interested in calculating. This right here is delta 1. So you can use the similar triangles here, and from the similar triangles you can write a relationship for delta divided by the overall height of this pole, which is 35 meters, is going to be your delta 1, which is this one, divided by this height, which is 20 meters. From here you can find the net displacement at the top as 26.9 millimeters.